Hi girls, in today's lecture we are going to see problems on least upper bound and greatest lower bound. Let us recall what is bounded above and bounded below set. Okay, so a set A contained in R is said to be bounded above if there exists an element n such that my each elements in my set will be what? Less than or equal to my n. Then I can say this is a bounded above set. And if this n is called the upper bound, okay, and any set A will have many infinite number of upper bound, and among that the least upper bound is denoted by L, and it will be least of all your ni's. Okay, and we'll say A contained in R is said to be bounded below if all the elements are greater than or equal to m. Okay, and there will be infinite number of lower bounds. M is also a lower bound, and we'll see that they will take the greatest of all the lower bound to be small l. Okay, this definition and all we have seen in the previous lectures. Now just keep this in mind, and we'll see all the problems. The first problem is this: if A is a non-empty bounded subset of R, it is given that A is a non-empty and it is bounded subset, and GLB for A is equal to LUB for A. Okay, it is given that GLB and LUB are equal. Okay, so what can you say about A? Okay, it is given A is a bounded subset. It is given bounded. Bounded means least upper bound and greatest lower bound will exist, isn't it? And they are telling the least upper bound and greatest lower bound is equal. Okay, then what will be your set? Obviously, the set will contain only one element. Okay, isn't it? If the set contains only one element, the least upper bound is what? 2. Greatest lower bound again 2. Okay, so if it is a singleton, then this is possible. Okay, we'll see that. Let the least upper bound of A to be L, take the greatest lower bound for A to be M. Given what L and M are equal. By least upper bound definition, we will be having x is less than or equal to L. By the definition of greatest lower bound, M is less than or equal to x. Okay. So I can rewrite this as M less than or equal to x less than or equal to L. It is it M less than or equal to x less than or equal to L. Okay, from this what can I say? We know what is least upper bound and greatest lower bound are equal, isn't it? They are equal. It is given in your problem statement. That means I can replace this M by L itself, and that means what? My x and x will be equal to L. Okay, we have an element x which is an element L which is less than or equal to x as well as greater than or equal to L, means obviously both will be equal. That means x is equal to L is equal to, we already know L is equal to M. Now we have proved x is equal to L. When you combine these two, you will be getting x is equal to L is equal to M. That means the set A is a singleton set. It will have only one element. Okay, it will have only one element. Yes, so we'll see the next problem. Find greatest lower bound and least upper bound for the following set. It's very simple. Since it is an closed interval, 7 and 8 are included in our upper bound and lower bound. So here my least upper bound is obviously what? It is 8, and greatest lower bound is obviously 7. We can see from the problem itself we can identify, but we have to prove this theoretically. Okay, we'll see how. Given x is less than or equal to A, my elements are less than equal, less or equal to a, isn't it? We have taken what? Closed interval 7 comma 8. Therefore my elements will be what? It will be less than or equal to 8. 8 is the, which means that 8 is the upper bound for the set by the upper bound definition. Okay, if possible, let me take a small difference, an element which is less than 8 to be 8 minus epsilon, which is also an upper bound of a. Let me take it. Okay, then all the elements of a will be what? Less than or equal to 8 minus epsilon. What does it mean? The least of all the upper bound is 8, we know, but now I am getting 8 minus epsilon to be the upper bound, which is not at all possible. Therefore 8 minus epsilon is not an upper bound, that is, there is no value less than 8 to be the upper bound for the set. Okay, so 8 is the only upper bound and it is the least among all the upper bounds. Okay, to find the lower bound, again the same story you have to do. Okay, for the from the bounded above, greatest lower bound definition, I can write 7 is the greater, less than or equal to x. All the elements in my set are greater than 7. Okay, that means what? 7 is the lower bound, which is the greatest of all the lower bound. Okay, we have to prove that. So 7 is the lower. Suppose there exists 7 plus epsilon to be the lower bound. Okay, 7 plus epsilon to be lower bound means 7 plus epsilon will be less than or equal to all the elements of A. Okay, but we have an element R, means 7, which is still lesser than 7 plus epsilon, isn't it? So 7 plus epsilon is not greater than 7. Therefore 7 plus not is the 7 plus epsilon is not a lower bound for A, which means 7 is the only, no member greater than 7 is the lower bound. That means 7 is the only lower bound which is the greatest. Okay, so in this problem, the closed interval 7 comma 8, the greatest lower bound is 7 and least upper bound is 8. Suppose if it is an open interval 7 comma 8 like this, then the greatest lower bound is 7 only, but it is not in the set. And greatest lower bound is least upper bound is 8, which is also not in the set. Okay, and greatest lower bound is 7, which is also not in the set, but it has least upper bound and greatest lower bound. We already saw in a previous lecture, the least upper bound and greatest lower bound need not be in the set. If it is an open interval, it is not in the set. Okay, yes, we'll see the next problem. Find the least upper bound and greatest lower bound for the set. My set is this: pi plus 1, pi plus 2, pi plus 3, and it will go on. So the set is of increasing order, isn't it? It is like positive integer 1, 2, 3, 4, like that, isn't it? Therefore it is bounded below, but it is not bounded above, isn't it? Since it is in increasing order, it is not bounded above. Therefore I cannot find least upper bound, but I can find greatest lower bound. Okay, so let me take an element between pi plus 1 and pi plus 2. Let it be pi plus 1 plus epsilon. Okay, so we know that from the set, we know that pi plus 1 is the least of all the elements. So pi plus 1 will be less than or equal to x. That is the lower bound for my given set A. Now let me take pi plus 1 plus epsilon to be the lower bound. Okay, if possible, pi plus 1 plus is also a lower bound. Then we should have what? Pi plus 1 plus epsilon is less than or equal to all the elements of A. Will it happen? No, because my pi plus 1 will be greater. It is not less than my pi plus 1 plus epsilon. Okay, therefore there is no element of A which is greater than pi plus 1 to be a lower bound. Therefore pi plus 1 is the greatest lower bound. Okay, we'll see the next problem. Find the least upper bound and greatest lower bound for pi plus 1, pi plus 1 by 2, etc. Okay, now this pi plus 1, pi plus 2, 1 by 2, pi plus 1 by 3, my last element will be what? Pi plus infinity, isn't it? Okay, So my elements here to find, first let me find the least upper bound. My elements pi plus 1 is the greatest element, isn't it? Because it is reducing. 1 by 2 means 0.5, 1 by 3 means what? 0.3333. We are reduced, the numbers are getting reducing. Pi plus 1, pi plus 1 by 2, pi plus 1 by 3, it is reducing, decreasing order. Okay, so it is in decreasing order, but it is not tends to infinity. Okay, at last what will happen? 1 by n, when n tends to infinity, it will become 0. My last element will be what? Pi. Okay, though this is a bounded set. Okay, we can find least upper bound and greatest lower bound. Okay, so my greatest of all the element will be pi plus 1. So my pi plus 1, my each elements in the set are less than the pi plus 1. That means it is bounded below by, it is bounded, upper bound for the set will be what? Pi plus 1. Okay, my bounded above by pi plus 1, upper bound. So let me take some lesser than this, that is pi plus 1 minus epsilon is also the upper bound. Then all the elements in the pi plus 1 minus epsilon must be, all the elements must be less than or equal to pi plus 1 minus epsilon. Is pi plus 1 is less than pi plus 1 minus epsilon? Obviously not, it is not at all. Therefore, this is upper bound, this pi plus 1 minus epsilon is an upper bound, is not possible. That means pi plus 1 is the only upper bound for A, that is the least of all the upper bounds. So, least upper bound will be what? Pi plus 1. Okay, yes. Now I have to find the greatest lower bound. To find greatest lower bound, as I said before, this pi plus 1, pi plus 1 by 2, pi plus 1 by 3, it will go on. That at nth stage it will be pi plus 1 by n. So if it tend n to infinity, then it will become pi. So at the last element in my set will be what? Pi. Okay, pi is the last element, then every element in my set will be greater. Okay, therefore I can write pi is less than equal to x, which resembles this. M is less than equal to x. That means the set is bounded below and M is the what? A lower bound. Okay, here by that definition here my pi is the lower bound. Now since again you have to prove theoretically, I am going to take pi plus epsilon also a lower bound. Pi plus epsilon means and that means pi plus epsilon must be less than or equal to all the element, but my pi is the least of all the element. I cannot have pi plus epsilon to be lesser than pi. Therefore, this is not possible. Therefore, pi is the only lower bound. Therefore, pi is the greatest of all the lower bound. So, greatest lower bound of A will be pi. Okay. And next example is, give an example of a countable bounded subset A of R whose least upper bound and greatest lower bound and least upper bound are both in R minus A. Okay, give an example of countable bounded subset A of R. Okay, it has to be a bounded subset of A of R such that R minus A okay. So my greatest lower bound and least upper bound must be in R minus A. We'll see. Let A be the set of all rational numbers between two irrational number root 2 and root 3. Root 2 and root 3 are irrational, we know. We can find the infinite number of rational numbers between these two, isn't it? So take that elements, the set of all rationals between root 2 and root 3. Now the rational number, so what is A? Rational number intersection root 2 comma root 3. It's open interval. That means you are not considering root 2 and root 3. We are considering only the elements between root 2 and root 3, and we are considering only the rational numbers, and we are taking that to be A. Okay. Now I have to find the least upper bound. So since root 3 is the last element, so obviously each element in my open interval root 3 comma 3 will be what? Less than or equal to root 3. What does it mean? Root 3 is the upper bound for the set A. If possible, root 3 minus epsilon is also upper bound, then there will be many rational numbers between root 3 minus epsilon and root 3. Okay, then all the rational numbers of the set A will be less than or equal to root 3 minus epsilon, but there exist rational numbers of A not less than or equal to less than root 3 minus epsilon. Therefore, root 3 minus epsilon is not an upper bound. So, no element less than root 3 can be an upper bound. That means root 3 is the only upper bound. That means that is the least of all the upper bound. So, the upper bound for A is root 3. Okay. So, similarly we have to find greatest lower bound. So, in the open interval, root 2 is the least lower bound. Let me take root 2 plus epsilon to be the lower bound. That means what? All the elements will be root 3 plus epsilon is the least and all the elements will be greater. Okay, but there can be rational numbers between root 3 plus epsilon and also root 2, which is not possible because we have assumed that root 2 is the lower bound. Now I am finding root 2 plus epsilon to be a lower bound. Therefore, no elements greater than root 2 are the lower bound. That means root 2 is the only lower bound. That is the greatest of all the lower bound is root 2. Okay. Now remark, by least upper bound axiom, for any subset of a real number which is bounded above will have least upper bound, and the least upper bound is also a real number, but this does not happen for a subset of rational number. Okay, so by least upper bound axiom we know that there exists a least upper bound and that is also a real number. Okay, but this is not true for rational number. Sometimes the least upper bound and greatest outer bound may be a rational number. Okay, so that is, if A is a subset of rational number which is bounded above, its least upper bound exists, but it need not be a rational number. So we have seen the previous example, isn't it? The least upper bound and latest lower bound for the set are not rational, it is irrational, isn't it? So the set of all rational numbers has holes in it. We can say the set of all rational numbers have holes in it. We will see example for this statement. The set of all rational numbers has holes in it. So now consider the set 1 plus 1.4, 1.41, 1.414. Each of the numbers of A is the rational number. Yes, because I can write it as 1, 14 by 10.